Welcome to Spring LIB.
Okay, so problem number 28 gives a series of reactions, and it wants to know if these reactions and decay pathways are possible, and if they are, why, and why, or if they're not, why not? So what we need to do is we need to look at each one of these individually. So for A, we have the reaction. We have a pi meson plus a proton decays into a neutron plus an eta baryon. Now, so what we need to do now is use the conservation laws to see if this is allowed. So first, let's look at charge. So for charge, all right, you have the charge of a pi meson is -1. The charge of a proton is 1. So that should equal to the charge of a neutron, which is 0, plus the charge of a neutral aton is 0. So -1 plus 1 is 0, is equal to 0 plus 0. So charge is conserved. Write that a little better. Conserved. All right, so now let's look at the baryon number. Baryon number. All right, so the baryon number of a pi meson is 0, plus the baryon number of a proton, which is 1. Is that equal to the baryon number of a neutron, which is 1, plus the baryon number of a eta meson is 0. So 0 plus 1 is equal to 1 plus 0. So the baryon number is conserved. Let's look at the lepton number. All right, so the lepton number of the pi meson is 0. Lepton number of the proton is 0. It's equal to lepton number of a neutron is 0, plus the lepton number of an ation is 0. So the lepton number is conserved. Now, the strangeness number. Strangest number of a pi meson is 0. Strangest number of proton is 0. Strangest number of a neutron is 0. Strangest number of the ation is 0. So this is also conserved. So this reaction is allowed, but I want to make a point that if we look at the conservation of mass energy, so you have the mass energy of a pi meson, 139.6 MeV, plus the mass energy of a proton is equal to 938.3 MeV, equal to the mass energy of a neutron, which is 939.6 MeV, plus the mass energy of an ation is 547.5 MeV. So these do not equal. So mass energy would only be conserved, and this reaction would only be possible if these collide with enough kinetic energy to do so. All right, so now for B, we are given the reaction pi meson plus proton reacts into a neutron plus a neutral pi meson. So let's look at first charge. So we have charge of the positive pi meson is 1. Charge of a proton is 1. Does this equal to this charge? So well, neutron is 0. The neutral pi meson is 0. So these do not equal, so therefore it is not conserved. Not. conserved. So this is not an this reaction is forbidden because of conservation of charge. Okay, now for the next reaction, part C, we're given a positive pi meson plus a proton goes to a proton plus a positron. All right, so let's see. For the charge, let's look at the charge conservation. We have 1 plus 1 is equal to 1 plus 1. So charge is conserved. So let's look at the baryon number. The baryon number. So for the baryon number, we have 0 for the pi plus 1 for the proton goes to 1 for the proton plus 0 for the positron. So this is also conserved. So now let's look at the lepton number. All right, so we have the pi, which is 0, and the proton, which is also 0. I keep doing that. That should be an equal sign. Does this equal to the other side? So for a proton is 0. For a positron, it's equal to 1. So these do not equal. So this is not conserved. Therefore, this is a forbidden reaction because of conservation of lepton number. So now for the fourth reaction. D, we have a proton decays into a positron plus an electron neutrino. So let's look at charge. We have 1 is equal to 1 plus 0. So charge is conserved. Charge is conserved. Now let's look at the baryon number. So proton is a baryon, so that's 1. Is that equal to what we have on the other side? Well, a positron is 0, and an electron neutrino is also 0. I don't know about that. It's also 0, so these do not equal, so not conserved. And so this is forbidden because the baryon number is not conserved. Conserved. All right, so for E, we're given a muon decays into an electron. I'm sorry, a positron plus an anti-muon, an anti-neutrino, an anti-muon neutrino. Sorry, an anti-muon neutrino. There we go. All right, so let's look at charge. So we have 1 for the muon equals 1 for the positron plus 0 for the muon, for the neutrino. So that's conserved. Conserved. Now we'll look at the baryon number. We have 0 for the muon, 0 for the positron, 0 for the neutrino. So that's also conserved. Let's look at the lepton number. All right, so we have 0 for the muon is equal to 1 for the positron plus 0 for the neutrino, because even though the neutrino has a lepton number, if you look at table 2, the neutrino does have a lepton number, but it has, this is a mu neutrino, not an electron neutrino. So it's an it's a mu antineutrino. So it has a mu lepton number, not a electron lepton number. So it's different. So if this were an electron antineutrino, this would be -1, and then the lepton number would be conserved. But since it's the electron lepton number of the mu antineutrino is 0, just like the mu lepton number of the positron is 0. So so this does not. So this is not conserved. So that way, so that's not equal. It's not conserved. So this is forbidden due to the lepton number. So yeah, you have to pay attention with the lepton numbers, because different species of leptons have different lepton numbers. So it's the like an electron has an electron lepton number, a muon has a muon and a lepton number, and a tau has a tau lepton number. All right, so part F, we are given the reaction, or the decay, that a proton, so this is F, a proton decays into a neutron plus a positron plus an electron neutrino. Okay, so first thing I'm going to do, I'm going to look at mass, because in the past I looked at the other 4 conservations first because they're a little easier to tally up. But this one, a neutron is heavier than a proton. So instinct tells me that if you add up a neutron, a positron, and a neutrino, your mass energy is going to be higher in your products than in your in your reactant. Your decay products are going to have a higher energy than your decay reactant, starting particle. So this is only allowed, this only happens if you have a collision in which the kinetic energy makes up for the difference in energy, the products having higher energy. So let's go ahead and do this real quick. So the mass energy, we have the mass energy of a proton, which is 938.3 MeV per c squared. Does this equal to the neutron, 939.6 MeV per c squared, plus an electron, a positron, sorry, which is 0.511 MeV per c squared, plus 0, because a neutrino is massless. So we can already say that that is not conserved. So this is forbidden due to mass energy.